Hi, welcome back to my class in number theory. For today, we will take up some basic or elementary divisibility properties. First, we start up with definition of division of integers. What it means to divide an integer by another integer, or what it means when we say that an integer x divides an integer y. But before that, I would like to point out one very important notations that we will use throughout the course beginning from today. The small letters of the English alphabet, A, B, C, up to letter Z, we will use them to represent integers. So if these letters A, B, C up to Z are integers, they are elements of the set C, capital letter C, the set of integers, which consists of the negative integers, the zero integer, and the positive integers. Thus, whenever you see in definitions, in theorems, and in our discussion, some small letters of the English alphabet, without saying that they represent integers, we will take them as integers. Now we define division. This notation is read as B divides N. And B divides N means, as I said, B divides N if there is an integer x denoted by x such that N is equal to B multiplied by x. And this notation with this vertical line with a line across it, with a small line across it, this is read as B does not divide N. And B does not divide N means that B divides N is false. In this definition, the letter D is an integer, letter N is an integer. And when you say B divides N, and you want to write that in notation using division, we write it this way. When we say D divides N, if you write that in this notation using the operation division, D divides N, which means that N is divisible by D, which means that N is exactly divisible by D. We can divide N by D, and the answer is an integer, another integer. In the definition, D is an integer, N is an integer. So D divides N if there is an integer x such that N equals D multiplied by x. If we can divide the integer N by the integer D, then the answer is another integer. And we denote that integer by x. If B divides N, or the integer N is exactly divisible by the integer D, there is some integer x. That is the answer to N divided by D, or D divides N. And from this equation, if you cross multiply D by x, if you cross multiply D by x, you will get N equals D multiplied by x. But this will only be true if there is some x, which is the answer to the division n over d. So we say d divides n if there is some integer x such that if d is multiplied by x, the answer is the integer n. And this is what we have in the definition, n equals dx. And if d does not divide n, denoted by this notation, then there is no integer x such that n is equal to dx, or we simply say d divides n is false. Again, you take note of the following. I already told you that we will use the small letters of the English alphabet to denote integers, elements of the set of integers C. Now, this notation d divides n can be read in several ways. This notation can be read as d divides n. Another way to read this notation is d is a divisor of n. Because n is exactly divisible by d, or n can be divided exactly by d, then d is a divisor of n. Another way to read this notation is d is a factor of n. From this equation, we see that n equals dx if d divides n, there exists an integer x such that n equals dx. Hence, we have expressed n as the product of two integers, d, integer d, and integer x. And both of these integers are factors of n. And we are very sure that d is a factor of n. D is a factor of n because d divides n. And another way to read this notation is by saying n is a multiple of d, because here we have expressed n as the product of the integer x and d. Therefore, n is a multiple of d. We will now take some examples. For example 1, consider this. We read this as 3 divides 12. Again, this notation is read as 3 divides 12. And that is true because if we actually divide 12 by 3, 12 is exactly divisible by 3. We can divide 12 by 3 and the answer is another integer, which is the integer 4. Hence, 3 divides 12 because there is an integer 4 such that 12 is equal to 3 multiplied by 4. From our past lesson, we use this notation or symbol to denote such that. Hence, this 3 divides 12 is true because there exists an integer 4 such that 12 is equal to 3 multiplied by 4. In our definition, our n in this example is 12 and d is 3. We use the small letter d in the definition because in this notation, the first integer or the denominator here is the divisor. Now, this notation, instead of saying 3 divides 12, can also be read as 3 is a divisor of 12, which is true because 3 divides 12. And the answer is 4. Another way to read this notation is by saying that 3 is a factor. 3 is a factor of 12 because there exists an integer 4 such that 12 is equal to 3 multiplied by 4. Now, we have expressed 12 as a product of of two integers, 3 and 4. And each of these integers is a factor of 12. Thus, 3 is a factor of 12. And another way to read this is by saying that 12 is a multiple of 3 because 12 can be written as a product of 3 and another integer. And 12 can be divided exactly by 3. Therefore, 12 is a multiple of 3. Now, 2 does not divide 7, and we use this notation to indicate that 2 does not divide 7. And this notation means that from our definition, this notation which we read as 2 does not divide 7 means that 2 divides 7 is not true, or 2 divides 7 is false. Because if you try to divide 7 by 2, there is no integer. You can divide 7 by 2, but the answer is not an integer. The answer is 3.5. And 3.5 is not an integer. 3.5 is not the element of the set of integers. And you remember that in number theory, we will deal only with the set of integers. As we said, the set of integers are the building blocks of the course number theory. Yes, we can divide 7 by 2. The answer is 3.5, but 3.5 is not an integer. So we say 7 is not exactly divisible by 2. And we say that 2 does not divide 7, written in this notation, because you cannot find an integer such that an integer k such that 7 is equal to 2 multiplied by that integer. This integer k does not exist. When you multiply it by 2, the answer is 7. So we conclude that 2 does not divide 7. Again, 2 divides 7 if we can find if there is an integer k such that 7 is equal to 2 multiplied by the integer k. But k does not exist. There is no integer k. When you multiply it by 2, the answer is 7. Thus, we conclude that 2 does not divide 7. And again, in the definition, 2 does not divide 7 means that 2 divides 7 is false. And we have shown that this is true. 2 divides 7 is false because we cannot find an integer k such that 7 is equal to 2 times that integer. There exists no integer k that satisfies this equation. Or when we actually divide 7 by 2, the answer is not an integer element of the set C of integers, but the answer is 3.5. So we conclude that 2 does not divide 7. That is exactly. Yes, we can divide 7 by 2. It's 3.5. But in the definition that says that D divides N exactly. That means if you divide the number n, the integer number n by the integer d, n is exactly divisible by d. And that is what is meant by d divides n. But here, 7 we can divide by 2, it's 3.5, but the answer is not an integer. We say that 2 divides 7, 2 divides 7, if the answer in this division, 7 divided by 2, is an integer. But the answer is not an integer, and we cannot find an integer k that will satisfy this equation. Therefore, 2 does not divide 7. In example 1, 3 divides 12, because if we actually divide 12 by 3, the answer is 4. So there is at least one integer, and actually there is only one integer. 4 with this property, 12 equals 3 multiplied by that integer, and that integer is 4. Now we will state 3 other alternative definitions for D divides N. We have 3 other definitions of this notation, D divides N. The first alternative definition, D divides N, means that N equals dk for some k. That means the integer number N is divisible by, can be divided by the integer d if there exists some integer k, such that the number n is equal to the product of d and the integer k. Now this symbol, if as we have taken in your course in mathematical logic, is the double implication. And this definition is actually equivalent to 2 statements. If D divides N, as I said, this double implication results to 2 equivalent statements, is equivalent to 2 statements. The first statement, D divides N, implies, or if D divides N, then there is some integer k such that n is equal to dk. Implies. And the converse of this statement is also true. If n equals dk for some k, then we conclude that d divides n. The other statement equivalent to this definition, to this statement in the definition is, if n equals b times k for some integer k, if this is true, then this implies that b divides n. Again, this double implication is equivalent to two statements. The first, b divides n, implies that exists some integer k such that n equals b multiplied by k. And the other statement is for some integer k, n equals b times k, then this implies that b divides n. But these two statements, statement 1 and statement 2, can be combined as a single statement, resulting to double implication. The second alternative definition for d divides n is given by this definition: d divides n if and only if n equals bk for some k. Now this, as you have taken in your course in mathematical logic, is a biconditional statement, which is also equivalent to two statements. The biconditional statement is always equivalent to two statements. The first statement equivalent to this biconditional statement, d divides n if and only if n equals bk for some k, is this statement: if d divides n, then n equals b times k for some integer k. And the second statement is the converse of the first statement. For the converse of this statement, you now start with the conclusion, and the premise becomes the conclusion. If for some k, n equals b times k, then we conclude b divides n. And again, as in biconditional statement, as in the double implication statement, we can combine these two statements and we will get this biconditional statement with if and only if. And the third alternative definition for d divides n is given by the following. The third alternative definition for D divides N is given by this statement. D divides N if N equals D times K for some integer K. Now, the if here in this definition, without saying it, is taken to mean the biconditional if and only if. If you would state the definition of D divides N in this way or in this form, D divides N if N equals D multiplied by K for some K, then the if here would be taken to mean if and only if, without you saying that your if in this definition means if and only if. And that is true for most definitions in mathematics. Many or most of the definitions in mathematics are stated as biconditional statements or as if and only if statements. Now we will take the elementary divisibility properties. The elementary divisibility properties are stated as a theorem. Theorem: if N, M, and D are integers, then the following statements hold. That means in the following statements are true if for all integers N, M, and D. The first property, the first divisibility property states that N divides N. And N here is an integer. And this means that everything divides itself, which means that every integer divides itself. Or every integer element of the set C is divisible by itself. And we prove this first property by definition of divisibility. We say that N divides N means that in our definition, we use the notation D divides N. But in the first property, the divisor D or the factor D is the same as the integer N. And from the definition of D divides N, N divide N means that the number N here can be written as the product of the divisor, which happens to be N also, times the integer K for some K. Now what you have to show is there exists an integer K such that this equation is satisfied. And if you cannot find that K, that integer K, then this is not true. And N does not divide N. And you will write that as using this notation. Again, to show that N divides N, you must find an integer K such that this equation is satisfied. If you cannot find that integer K, then you conclude that N does not divide N using this notation. But from this equation, we have N equals n times k. From this equation, we can derive this equation, k equals n divided by n, as long as n is not equal to 0. So n equals nk implies that k equals n divided by n. But a non-zero integer divided by itself is equal to 1. Thus, we have shown that n is equal to nk if the integer k is equal to 1. Because there exists some integer k, specifically k is 1, such that n equals n times k, or n times 1 is n. Then we conclude that n divides n. And this completes the proof of the first property, n divides n. Everything divides itself for all integers n that are not 0. Because we have shown that by definition n divides n means that we can write n as the product of n and an integer k. And we have shown that there exists an integer k which is 1, such that this equation is satisfied. Therefore, we conclude that n divides n. We now state the second property of divisibility, known as the transitivity property or transitive property. We state the second divisibility property, known as the transitivity property or transitive property. Transitivity or transitive property states that if n divides m and m divides d, then n divides d. In this transitive property, there are two given in the premise. The first given is that n divides m. The second given is that m divides d. And we will use both of these two given to prove or show that n divides d. We now prove this property. We start with the first given, n divides m. The first given is n divides m. Since n divides m, then by definition of divisibility, there exists some integer k1 such that the number m is a multiple of n. That is, the number m is equal to and the divisor n times the integer k1. That's by definition of divisibility. And we now use the second given, m divides d. Because we are given that m divides d, there exists some integer k2 such that the number d is equal to the divisor m multiplied by the integer k2. And we are sure that these integers k1 and k2 exist because we are given that n divides m and m divides d. And we will make use of these two equations to show that n divides d. We want to show that n divides d. And to show that n divides d, we must show that there exists some integer k such that the number d is equal to the product of the divisor n and that integer k that we are looking for. And we will make use of these two equations to find this integer k. We have d equals m multiplied by k2. And in the first equation, m equals n times k1. In the second equation, we replace m with n times k1. We replace m with n times k1. And our reason here is by substitution. Now we have d equals n quantity n k1 multiplied by k2. Again, d is equal, the integer d is equal to quantity n k1 times k2. These are small letters, so they represent integers. N is an integer, k1 is an integer, k2 is an integer. And one of the properties of multiplication of integers is associative property. So we can group k1 and we can take k1 and k2 as one group, and we write d equals n times quantity k1 times k2 by associative property for multiplication. By associative property for multiplication of integers, this product quantity n k1 times k2 is equal to n times quantity k1 and k2. In this product, you have this first group n times k1, but in this product you have the group k1 times k2, but the products are the same and equal. Now, k1 is an integer, k2 is an integer, but the set of integers is closed under multiplication, which means that if you multiply two integers, the product is another integer. If you multiply two integers, elements of the set of integers c, the product of these two integers is also an integer, another element of the set of integers z. And that's by closure property of multiplication. The closure property of the set of integers under multiplication. So if k1 times k2 is another integer, we will denote that integer by k. The integer k is the product of the integers k1 and k2. And that's by closure property of multiplication. Again, because k1 and k2 are integers, the product of k1 and k2 is another integer by closure property. And we write, by closure property, k1 times k2 is element of c. Since k1 and k2 are elements of c. Since k1 and k2 are elements of c, if you multiply k1 and k2, the product k1 times k2 is also an element of c by closure property. Now we let this product, which is another integer, to be equal to k. So k is an integer. It is the product of k1 and k2, which is element of z. We specify k equals k1 times k2 is an element of z. Again, we let the product k1 times k2 be equal to k. Since k1 and k2 is an element of c, then k is an element of c. And k in particular is equal to k1 times k2. Now from the last equation we now replace k1 times k2 by k. Therefore d equals n times k1 times k2 equals k. Hence we get d equals nk. Therefore, we have found the integer k such that d equals n times k, and the integer k is the product of the integers k1 and k2. Therefore, we conclude that n divides d. By definition of divisibility, n divides d if there exists some integer k such that the number d is equal to the product of the divisor n and the integer k. And in this example, in this property, the integer k is the product of the integers k1 and k2. And that completes the proof of the transitivity property as indicated by this small shaded circle, small shaded square or rectangle. For your practice, please do the following exercises. Prove the following. Number 1, if 3 divides x and x divides y, then you prove 3 divides y. The given here are 3 divides x, and you use the definition of divisibility. And the other given is x divides y. You use again the definition of divisibility. Use those two given to prove this 3 divides y. For number 2, if A divides 20 and 20 divides B, then you prove that A divides B. Again, you have 2 given in number 2. A divides 20. That means there exists some integer k such that 20 is equal to A times k times that integer. The other given is 20 divides B. By definition of divisibility, there exists an integer such that the number B is equal to the divisor 20 times that integer. And you make use of these 2 given to prove that the integer A also divides the integer B. And we will continue with elementary divisibility properties in the next lesson and with their proofs. And if you have questions about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Calism, the channel of learning and leisure. Or you may also ask your friends, classmates, and neighbors to subscribe to my YouTube channel so they may learn as well. Thank you for joining me in my class today.